atom's electrons govern most of the everyday world. Electrons are a swirling cloud of negatively charged matter that can act as particles or waves. But how are electrons arranged? And how were those arrangements discovered? Niels Bohr proposed that electrons were particles that circled a nucleus in shells that determine their energies.
Niels Bohr decided that the lowest energy shell of an atom had to have 2 electrons by basically looking at the periodic table. He saw that helium was an incredibly stable element and that had 2 protons and thus must have 2 electrons. Since it was stable, it must have a full shell, hence 2 electrons.
The lowest energy shell is called n equals 1, and the next energy shell is called n equals 2. The number of electrons required to fill an atom's energy shells was first worked out by extending Bohr's ideas about helium to the other noble gases. All of these gases are very stable, which means that they do not gain or lose electrons readily. Bohr and others suggested that these gases must have energy levels that are filled and can take no more electrons.
Every atom can be described by 4 quantum numbers. And only 2 of them are really important to this discussion. The first one is called n. That's the principal quantum number. And n can be any number from 1 to any integer number. N actually goes up to 7. When n equals 1, that's the innermost and least energetic shell of an atom. When n equals 2, it's a little farther away from the center of the atom, and when n equals 3, farther still. And not only is the distance increasing, but so is the energy of each of those levels. So as an atom gets bigger, its electrons contain more energy. That's the principal quantum number. The next quantum number is called the angular momentum quantum number, and it's usually abbreviated with the Greek symbol L. And that can take on numbers from 3 different numbers, because it's an orientation phenomenon, and there's 3 different ways that something can be oriented in 3-dimensional space. The angular quantum number is sometimes confusing because it's often referred to with the letters S, P, D, and F. And most people's reaction is, what do those mean? And it's actually derived from old, probably 100-year-old spectroscopy, where there were sharp, principal, diffuse, and fine lines, S, P, D, and F, lines in the spectrum of the atoms. But the S one is the lowest energy, and it really describes the shape of an orbital which contains 2 electrons. The S orbital is round. The next is the P orbital, and the P orbital is shaped more or less like a dumbbell. And in quantum mechanics, people will be familiar with the concept of the Heisenberg uncertainty principle, which means that you can't know both the position and the velocity or the momentum of a particle at the same time. So if you know the velocity, which you do usually know about an electron, you don't know exactly where it is. And that's why the orbitals, the S, P, D, and F orbitals, are really distributions. The electron could be anywhere in those orbitals.
Knowing the energy levels of the orbitals enables us to begin building the periodic table, atom by atom.
The video that you just saw transitions you into the ideas of the quantum model, in that the electron is not in a fixed orbit but is in a probability region called an orbital. And that's the primary difference between the Bohr model and the quantum model. The Heisenberg uncertainty principle tells us that we cannot simultaneously know the position and the velocity of the electron. Instead, we have to look at probability maps, and these are called orbitals. We have 4 quantum numbers that describe the location of any electron, and I'm only wanting you to know 2 of them. I would like you to know the principal quantum number, n. It relates to the energy level of the electron, and it corresponds to the 7 rows of the periodic table. So we'll say, for our purposes, n can be 1, 2, 3, 4, 5, 6, 7. The other quantum number that I want you to know is L, the angular momentum quantum number, and it relates to the shape. We have 4 basic types of L values, 0, 1, 2, 3, but also known as SPDF. So when you have the first lowest energy level, the only shape of orbital is S, which looks like the sphere. That's S. When you're in the second energy level, you can have S or P orbitals, and the P orbitals are dumbbell shapes, and they can be on the X, the Y, or the Z axis. So it's PX, PY, PZ. And then you can have, in the third energy level, the Ds will first show up. And there are 5 orientations of d orbitals. And then once you get into the fourth energy level, it's possible to have Fs, and there are 7 different shapes of F orbitals. We only need this many quantum numbers to define all the elements that are known to man. What we're going to learn is how to place the electrons in the orbitals, and we have 2 different ways of doing that. One is called electron configuration, and here's the electron configuration for hydrogen. We list the orbital. It's the first energy level, the S orbital. 1 electron in there. That's all hydrogen has, is 1 electron, so we're done. The first electron of any atom always goes into 1s because it's the lowest energy state. This is the Aufbau principle, and let me spell that for you. Atoms look like the previous atom with the addition of another proton and another electron added in sequence. Aufbau, build up from 1s. Okay, so if I'm going to do lithium, if you look at the periodic table, lithium is the first element in the second row, so it has 2 electrons in 1s, and we have just started row 2, which gives it 1 electron in the 2s orbital. Here's the electron configuration of helium. It would be 1s2, and here's the lithium electron configuration that I just showed you. Alongside the electron configurations are the orbital diagrams. This is another way of representing the electrons. There's upside down arrows in 1s for helium. This is practicing the Pauli exclusion principle. Which says electrons will have opposite spins. If they must inhabit the same orbital, electrons will have opposite spins. We exemplify that by upside down arrows. It's our way of saying that electrons, because they're both negative, if they have to cohabitat an orbital, they would try to stay as far away from each other as possible. So here would be the orbital diagram for lithium. We're showing that 1s is filled with 2, and 2s has just 1 electron in it. This slide provides a visual ranking of energies. The first quantum number, n, corresponds to the energy level. And so we say 1 is the lowest energy, and 2 is the next highest, and 3 is the next highest. This also corresponds to atom size. 1s are the electrons closest into the nucleus. 2s electrons must exist farther out from the nucleus. 2p farther out still, etc. It's important for you to see that the 3ds are actually a little higher in energy than 4s. So we have the unique aspect that atoms that have electrons filling these orbitals will actually fill 4s before they fill their 3ds. And we'll explain that by the use of the periodic table. Let's now write more electron configurations, and I'm going to show you how to use the periodic table to do so. This is by far the easiest way for you to write electron configurations. The main thing you need to have in your mind is that this is the S zone, this is the P zone, this is the D zone, and this is the F zone. If you can have that in your mind with this important idea that when you hit the D's, go back 1 in energy level. And when you hit the F's, go back 2 in energy level. This is because of the diagram I showed you on the previous page, which showed that the S's are actually a little lower in energy than the D's of the prior energy level, and the F's are fill 2 energy levels later. So let's show this by example. Alright, I want to give let's just pick one of these. Let's pick gallium. Okay, I've got 31 electrons to place. So the first electron always goes in 1s, and it would be full. Here's 1s2. And I'm just going to go left to right across the table, and it will generate the electron configuration in a very systematic way. Alright, 1s is full, go down to the next row. Next I would fill 2s. 2 electrons would be in the 2s region, and then I come across, and now I'd fill the 2p's, and I'd have 6 electrons there. And now I'm going into the third row, and first thing I hit is 3s. Full, come across, 3p's would fill next. I would have 6. You see where I'm getting 6? 1, 2, 3, 4, 5, 6. And then I drop down a row and fill the 4 S's, and I'd have 2 electrons. And here's the little gotcha. Watch out when I hit the D's, go back 1 in energy level. This is the 3 D's filling. How many columns are in the D's? Well, I have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Full. And now I'm finally at gallium, and its last electron goes into 4p, and I only have 1 of them. This is the placement of 31 electrons for gallium. Let's do rubidium. When I look at rubidium, I basically know it looks exactly like krypton with the addition of 5s1. There's actually a shorthand we could use, and I'll just put that down here. The electron configuration of rubidium, we do bracket, krypton, and then we finish it off, 5s1. That's the shorthand. For now, I want you to do it longhand because you're just learning how to do this. So remember, this is the S zone, the P zone, the D zone, the F zone. Alright, starting with row 1, go across 1s2. 1 is full, drop down to row 2, 2s2, 2p6, drop down to row 3, 3s2, 3p6. I'm now in row 4, 4s2, 4s2, 3d10. Remember to drop back when you hit the D's. Now go up 1 because I'm back into the 4p's, and they're full. This is actually krypton's electron configuration, and now the finish of 5s1. This is the electron configuration of rubidium. If I were to do orbital diagrams, first of all, here's the electron configuration that we would generate for carbon. Let's go back to the periodic table, look at carbon sitting right here. You see it's 1s2, 2s2, 2p2. Orbital diagram-wise, we draw 1 line for s's and 3 lines for p's. So we do 1s2, 2s2, and they're full with up-down arrows. And then the 2p's we do line, line, line. And now we're going to practice something called Hund's rule. Hund's rule says these electrons don't want to be paired in the same orbital if they don't have to. They will spread out into the different orbitals, and so we see them going solo into 2 separate orbitals. It's not until we come across to oxygen that we have to double up any electrons, because this would be single, 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 and then this would be the first time we'd have to double up, and then we'll use Pauli exclusion principle to do up-down arrows for oxygen. Let me just show you how this whole thing charts out. Oh, this is another method some people use, but I find the periodic table so much easier. There's a zigzag pattern that maybe that works for you. Just want to show you the completion of the second row. Look at nitrogen. You have 1s2, 2s2, 2p3. Here's the orbital notation equivalent. 1s2, 2s2, 2p3, single, single, single. Now here's oxygen, which has 4 electrons in the 2p. So you can see now we do the upside down arrows in the first 2p. And then here is fluorine coming in, and it would be 1s2, 2s2, 2p5, and we double up and single. And then finally, here's neon with its super stable electron configuration. Everything's full with up-down arrows in each of the orbitals. The shorthand notation that I showed you for rubidium, here it is for sodium. Here's the drawn out electron configuration for sodium, 1s2, 2s2, 2p6, 3s1. Or you could say sodium looks exactly like neon with a 3s1 added on. And that takes us to the end of 9.6. Next we're going to talk about how all of these electron configurations are repeating in the periodic table, and that the valence count ends up establishing common chemical behavior which sets up the columns.